Hello everyone, my name is Yan Lin. I'm from Singapore Management University. Now I will introduce our work called When Function Signature Recovery Meets Compiler Optimization. As we know, an accurate CFI policy is a prerequisite to CFI enforcement. Most approaches rely on the availability of source code to get this kind of policy, such as modular CFI, PyCFI, and forward CFI. However, current binary level CFI techniques are weak in recovering the set of valid targets for indirect branch transfers. This is because the compiler will not preserve a lot of language level information, such as the type information in the process of compilation. Two approaches are proposed to recover the function signature through static binary analysis, and the recovered function signature can be used to help CFI enforcement. These two approaches are type armor and tau CFI, which recovers the number of arguments and widths of argument storing registers. For example, for this indirect corner, the recovered number of arguments is 3, and the recovered argument width is 32-bit for each of them. According to the recovered function signature, we can find the valid targets for this indirect corner can only be the first and third functions. Since the argument width for the second function is 64-bit, which is larger than 32-bit, it cannot be the valid target of this indirect corner. These two approaches rely on calling convention in Linux 64-bit to recover the function signature, in which integer arguments are passed in 6 argument registers, and they will collect state information on these 6 argument registers at the callee and the indirect corner site. Specifically, at the callee site, the forward recursive analysis is performed from the entry basic block, and at the indirect corner site, backward analysis is performed. They both assume that the argument registers are always reset between 2 function calls, so the analysis is terminated when a return edge is encountered. I will use an example to show how the number of arguments and argument widths are recovered. In this example, from the source code, we can find it has 4 arguments. After compilation from the binary, we can find 64 bits of the first 4 argument registers are read. So current approaches conclude that this callee has 4 arguments, and the width for each argument is 64 bits. But from the source code, we can find the type for the first argument is unsigned int, which is 32 bits rather than 64 bits. It means the recovered function signature from the binary is different from the source code. This is because during the compilation, the compiler optimization has a great impact on the function signature. We find 8 ways in which compiler optimization will impact function signature recovery. We call each of them as a complication case. Due to time limitation, I will only introduce 2 of them in detail. If you are interested in other complication cases, you can read our paper to get more details about them. First, we find many callees will not use all of their arguments. As shown in this example, we can find only the second argument is used by this callee. If we compile this callee without optimization from the binary, we can find it will always read the first 3 argument registers. So if we perform analysis for this callee, we can always get the correct number of arguments. But if we compile this callee with optimization, we can say only the second argument register is read. So if we perform analysis for this optimized query, we can find this query only has 2 arguments rather than 3 arguments. Another complication is the compiler prefers to use a smaller sized register to pass arguments at the corner site. For example, when arguments are constants whose sizes are up to 32 bits, arguments are pointers point to data section and text sections, and arguments are null pointers. As shown in this example, from the source code we can find the bases of the second and the third arguments are 64-bit respectively, but during compilation the compiler finds the actual value passed to them are less than 32-bit. So only 32-bit argument registers will be used to set the actual arguments. Finally, current approaches will conclude the basis for the second and third arguments as 32-bit rather than 64-bit. Another example is shown like this. The compiler finds the actual value passed to the second argument of this indirect corner is a null pointer, so it will use the exclusive OR instruction to pass the second argument, in which only 32-bit argument register is set. And the current approach will say the base for the second argument is 32-bit rather than 64-bit. We want to know how the 80 complications will present on real-world programs. So we use applications compiled by Clang and GCC with different optimization levels to perform a detailed analysis. In total, there are 552 C executables and 792 C++ executables. The tool we will perform evaluation include TypeHammer, TauSci, and a well-known binary analysis framework, Ghidra. The metric we used is the likelihood that the correlates and the indirect corners present a complication in the function signature recovery. Due to the time limitation, we only show the evaluation result for applications compiled by Clang. If you want to get more details about the evaluation result, you can read our paper. Here, the x-axis is the complication cases we identified, and the y-axis is the likelihood that these complication cases will present. At the query site, we can find many queries will not use all of their arguments, which is the biggest contributor that will impact function signature recovery, and it is more heavily in C++ programs. We also find current approaches are more likely to misidentify normal functions to value-added functions for unoptimized binaries. Here, value-added means the callees can accept a variable number of arguments, and Ghidra only simply considers all functions as non-value-added functions. We also find C++ programs are more likely to store the return value to the third argument register, which makes it more difficult to the current approaches to misidentify the read operation on the third argument register is reading an argument. At the corner site, we can find the argument registers are commonly used to store temporary values. Another interesting finding is compiler optimization helps determine the number of arguments. Ghidra only analyzes the basic block which contains the indirect corner, so it will cause the number of arguments to be underestimated. For the complication case IMM, we can find the likelihood increases upon the increase of optimization levels. After the detailed analysis, we can find this is due to heavier application of function inlining and loop unrolling. Since the complication cases commonly present in real-world programs, we propose some improved policies to mitigate them. Due to the time limitation, I will only show some improved policies. If you want to get more details about the improved policies we proposed, you can read our paper. The first policy is to identify whether the read operation on the third argument register is reading an argument. As shown in this example, we can find the first and third argument registers are read, but the ground truth is the read operation on the third argument register is to read the return value from this library call. In this case, the policy is if the first read operation on the third argument happens after a call to a library function, we will say this read operation is not read an argument. So in this case, we can conclude this callee only has one argument rather than three arguments. Another improved policy is to identify whether one argument register is used to store temporary value. In this case, we will also take into consideration the reading of registers, rather than just check whether one argument register is set. More specifically, if we find an argument register is moved to another argument register after a write operation, we will say this argument register is used to store temporary value. As shown in this example, we can find there is a write operation on the fourth argument register, and after the write operation, the first argument register is moved to another argument register. So we can say the first argument register is used to store temporary value and conclude this indirect corner only has 3 arguments rather than 4 arguments. We use the same dataset and the same metric to evaluate our improved policy. At the callee site, we can find our improved policy significantly reduce the chances of misidentifying normal functions to variadic functions. We can also find our improved policy can completely mitigate some complication cases. For example, our improved policy can accurately identify whether the read operation on the third argument register is reading an argument. At the corner sites, we can find our improved policy reduces the likelihood of overestimation on the number of arguments. We also find our improved policy guarantees that valid corners never inadvertently blocked. This is because our policy never underestimated the argument width. We also perform security evaluation on the set of callees allowed for an indirect corner. We show the result for 6 approaches. Here, AT means allows indirect corners to target any address-taken functions. IFCC is a source-level solution with function signatures capturing the number of arguments. LLVM-CFI is a source-level solution with more precise function signatures. From the result, we can find, compared to AT, TypeArmor, TauCFI, and our improved policy reduce the number of legal targets by about 20%, 49%, and 54%. In conclusion, we perform a systematic study on how compiler optimization would impact the function signature recovery, and we also propose improved policies to recover function signature more accurately. That's all about my presentation. Thank you.